units. So in astronomy, we deal with a lot of big numbers. And we're going to start with astronomy. So we need to be able to kind of understand how big numbers are packed up in scientific notation. Some of you guys are like, oh yeah, I got that. Some of you guys are like, oh, I wouldn't mind you reminding me. So we can pack up big numbers like this in scientific notation, and we can pack up small numbers like this in scientific notation. Those zeros, I mean, once you start to look at them, they kind of make your eyes go buggy. So that's what scientific notation helps with. So I think we'll kind of pick on those two as examples. So what I do, again, or I haven't know if I said it yet, but I am not a math teacher. But what I do is I find the decimal, which you would probably tell me for this big number, the decimal is right here, okay, after the 0. It's not hardcore put there, but it's implied. And then you move the decimal over to get a number between 1 and 10, basically. And you count how many places, so you go 1, 2, 3, 4, 5, 6, 7, 8, 9. That would give me 12.3, and I need to go one more, so 10. So if I put a decimal between the 1 and the 2, that gives me 1.23, and I needed to move it over 10 places. So 1.23 times 10 raised to the positive 10th places. Okay, so that's how you would pack up that big number. And then the catch is, if the number is small, like the other one, the fraction of a second, in chemistry we kind of deal with little tiny numbers. But it's a similar thing, but now I'm going to move the decimal to the right instead of to the left. And I'm going to count the number of times. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I move it between the 4 and the 7, then I have 4.721 times 10. And I had to move it 9 places. But since I had to move it to the right, it's -9. 10 raised to the -9th power. So if you see a number that has a negative power of 10, then it's a small number. If you have a positive power of 10, it's a big number. There you go, in a nutshell. Okay, so I'll give you a few minutes for you guys to do on the next slide, the answers. So go ahead and you do them and I'll do them. How's that? The first one looks familiar. these moved? Double check if we got some different, let me know, because yours might be right. It's kind of like balancing a checkbook, like multiple times, if multiple people do it, let's get the same answer for that. Okay. So I think magnitude is important because, like, we might be dealing with, you know, a star that is, you know, 5.3 times 10 to the 32nd, you know, kilometers away, and that's the ways. I think that's too close for a star, but just kind of threw that out there. Okay. So this next part, I don't think I necessarily want to emphasize it. Don't worry about getting your calculators out. Honestly, when we get to that part in chemistry, we'll kind of make sure we all bring our calculators that day and we kind of poke in numbers and make sure we can do scientific notation on your calculator. As you are contemplating a calculator for that unit, you can borrow one of mine, or phones have you can get a scientific calculator on a phone, like an app. But you couldn't use it for the test. Then you have to borrow mine. But you need to be looking for a calculator that has EXP, EX, EE, SCI, or times 10 to the X. So that you won't need it for astronomy or meteorology. Okay. So we'll be talking more about your calculators later. So don't worry about these. Oh, but do worry about that. So how are we doing with the textbook? Like, let's see, textbook. Are you guys been able to get the textbook and such? Okay. The reason I mention it is I went ahead and printed out. Oh, dang. Where's this? 23 to 24. Well, I thought I printed out. Okay, we'll just have to leave it this way because I thought I had answers to all these. I just had answers to one of these here. So, did you say? I don't mean to put you on the spot. Who doesn't have a textbook? Okay, good. If I email you the questions, will you get them emailed, like to your SCC email? Okay, I will do that. But you are going to need a textbook. Cool. All right, so I just emailed everybody, and I meant to. Okay, so these will be due. A question might be due. Question might be one of these due, and the answer is going to be Friday because that's our next lecture date. So these will be due Friday. Tomorrow we have lab, right? No, dang it. Yes, we do. Wait.
Tomorrow's Thursday, yeah. Isn't it?
Yes, tomorrow's Thursday, and yes, we do have lab. Thank you. Okay, tomorrow we have lab, and I just want to mention a little bit about the weather and all that. So for class and lab, now a test you might want to risk your life to get here, but for class and lab, don't risk your life to get here. You shouldn't risk your life to get anywhere like that. Okay, unless like somebody's having a baby or something, then you have to get to the hospital. But anyway, so tomorrow I'll assume that we're all going to be here. But if you can't come, you're worried about the roads, then just a quick note would be nice. And we'll kind of see what we need to do with that. The other thing about notification and stuff, or about roads, is if they don't cancel, which SEC's been pretty good at canceling. If they don't cancel, but I don't want to make the trip from Burlington, I will actually send you guys an email, okay, to let you know that I'm not coming because that's my life either. Okay, so check your email. Any questions about that? Okay. Cool. All right. I guess we are on to dun dun dun. I have another set of PowerPoint slides to give you. We are going to dabble in astronomy. This class is just enough to be, you'll learn just enough to be dangerous in all 5 of these subjects. So astronomy. I also teach astronomy and chemistry in a 16-week session. So it's interesting and a challenge for me to kind of bring it into a three-week or so session instead of 16. So hold on to your hats. Okay. So, to kind of put things in perspective, and this slide doesn't talk about perspective, but I think it's worth it. So, this is going to be the sun. This is the sun. Okay, works out pretty good. Okay. And of course, the Earth goes around the sun, orbits the sun. The Earth is one of 8 full-fledged planets. Of course, Pluto used to be a planet. That's a whole other story. That would be the 9th object out beyond Neptune. And they orbit the sun in kind of a plane, kind of disk. Okay. So the sun, though, is a member of, anybody know what the name of our galaxy is? It's candy bar. The Milky Way. The Milky Way, yep. We are, our sun is one of billions of stars in our galaxy. And so one of the things, a question has come up before, do I think that there's life maybe out there other than just our planet? And I say probably odds are in favor of it, simply because of the numbers. Because we think every star in our galaxy, most stars in our galaxy, has a system of planets that orbits that star. So hey, and are there other galaxies in the universe? So it's just kind of mind-boggling. But that's the real deal of it. One of the things we'll talk briefly about in physics is this idea of gravity. You know, we all have a sense of gravity. You know, I drop something, this thing's been dropped too many times, but if you drop something, gravity's going to make it fall. Okay? So actually, it's that force of gravity, that actually makes the planets stay in orbit about the sun. If gravity weren't there, a planet's going this way, okay? One of Newton's laws, he said, dude, if you're going in a direction like that, you're just gonna keep going in a direction like that. But it's gravity that makes this curve. So we're going this way, gravity makes this curve. So, this is actually a photo of, this is the International Space Station, which is, the word international is kind of an awesome thing to think about. Scientists play well with each other. Politicians, not so much. And it is, here's the Earth and here is the sun. Okay. One of the things about the sun, or I guess one of the things about us here on Earth, is if it was clear today and we were to look out and look at the sun, would we see any stars? No. And it's not because the sun is just so darn bright. It actually has to do with the Earth's atmosphere. The Earth's atmosphere takes that sunlight and ding, 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 pings it around and makes our skies blue. So anyway, if you're in outer space, you have that pinging around called light scattering. So to kind of put things in perspective, 1 year on Earth is 365 and a quarter days. So we have leap years, which kind of makes up an extra day, everybody's between days and all that. And then we have some other kind of fixes to our calendar. But it takes 365 days for the Earth to complete one orbit about the sun. What do you think about other planets? Okay, so we have planet-wise, we have Sun, Mercury, Venus, Earth, and then what comes after Earth? Mars, yep. And then the asteroid belt, and then what comes after Mars? Jupiter. What comes after Jupiter? Saturn, yep. What comes after Saturn? Uranus? What comes after Uranus? Neptune. Sounds like a good test question, doesn't it? But as it turns out, and this is one of another scientist called Kepler figured this out, the closer the planet is to the sun, the faster it moves in its orbit. You're like, well, of course Mercury is going to not take so long to go around the sun because its circle is smaller, its orbit's smaller. But literally, it has a faster velocity. That has to do with gravity again. So this is kind of a figure showing the Earth going around the sun. Of course, we're all about us, so we don't show little Mercury and Venus and Mars and all that. But An important term in astronomy is down here. Sometimes it's called plane of the ecliptic, sometimes it's just simply called the ecliptic. But that's kind of the disk that holds the planets as they orbit the sun, the plane of the ecliptic. Another thing about this figure, and we'll be talking more about it on, I think, the next several slides, is can you see this right here, kind of this little stub, is actually, and it's the invisible or imaginary axis of rotation of the Earth. So picture, this is the North Pole, this is the South Pole, and this is the Earth spinning on it. Okay, but its axis that it spins on is tilted. Okay, so, and it's kind of like a dance partner that kind of always keeps one side kind of like that. And I don't mean to pick on it, but can you see that little pink note over there? That is the star called Polaris. And the Earth's north axis of rotation is always, and it'd be hard for me to kind of do this, but always pointing up towards Polaris. So here we go. This is what you see on the slide. And it takes, what, 12 months in a year. So if you take 12 and divide it into 4 sections, okay, so 4 sections would be 3 months, right? So here I go. Actually, as it turns out, this is one of our what we call solstices, yeah. This is summer in the northern hemisphere. Okay, 3 months later, what comes after summer? Fall. What comes after fall? Winter. Not so much a fan. What comes after winter? Spring. Okay, and then 3 months later, over here. So that's kind of what's going on. And I have a slide to kind of describe this, but it's thought that as it was forming, the Earth's axis of rotation actually used to be at a right angle or perpendicular to the ecliptic. That's right, at a right angle. And that early on, and we have evidence of this on our moon. Have you ever seen how pocked up the moon is, like with all these craters? It got banged up. And during that kind of active time in the formation of planets and such, we got something about the size of Mars. I think they even call it Theia, maybe? And it basically came and whacked the Earth, and part of the Earth ejected into and kind of snowballed in Earth's orbit and became the moon. Is that not a beautiful story or what? I just love it. So too cool. They gave us a tilt, and we got the moon out of that one thing. So that's the Earth's tilted axis of rotation. All right. So as the Earth spins once every 24 hours, that's when we get the daylight and nighttime. Kind of had Earth issues, globe issues. So one of the things about the orbits of the Earth and the planets and the spins of the Earth, the rotations or spins of the planets, it's about counterclockwise, except for Venus. And Venus is just Venus is Venus. So counterclockwise, so I've been trying to, and sometimes I get my counterclockwise mixed up, but can you see as I've done this, I'm going counterclockwise. It's funny, with all these digital clocks, we're kind of losing the idea of how a clock goes, but I'm going counter to the numbers on the face of the clock. Counterclockwise. If you're looking down at the North Pole, it's about counterclockwise. So, okay, so there's the North Pole, so I'm going to go counterclockwise. All right, so that's the sun. Here's the Earth. Let's find us, since we're all that. Let's see. Is it going to work? I think I need. So this is East Coast, right? Good. West Coast. So, where does the sun set first, on the East Coast or the West Coast? Who's ahead in the time zones? The East. Yep, the East is ahead in the time zones. So if we kind of do this little marker right here as where the sun's going to set, okay, because the sun's there. This is daytime. This is nighttime. Okay, so here we go. East Coast gets sunset first. I'll turn this way you can see it. East, and then Central, Mountain, Pacific gets sunset. Okay, So we have these time zone things kind of going on. One thing about, I don't think I have this in my slides, but you might find this interesting, that, is this right? Yeah, this is right. That the Earth rotating on its axis once every day, and the day is 24 hours for us now. It didn't always used to be. Early on, when the Earth was just kind of forming a crust, because it used to be kind of ooey gooey, when it was forming a crust, the Earth spun, oh my gosh, I don't know, was it 2 hours, 3 hours? I don't know, but it took only maybe 3 hours to complete one spin. But it had slowed down over time. So, you know, taking that a little farther, doesn't it seem logical? And it would be true, it is true, that the Earth is slowing down a little bit more, a little bit more. So we're getting a little more time. If you want more time in your day, so that's why we experience day and night, because of the Earth's rotation. There's too many R's. We use, I like the word orbit. And when I say orbit, you're like, oh yeah, the Earth orbits the sun. But another word we use for orbit is revolves about the sun. Really? Too many R's. And I already kind of indicated this. Where's my axis of rotation? So here's my Earth's axis of rotation, and it's tilted. And its tilt always points towards the Earth. Okay? And the amount that's tilted is actually, and I've read recently in another one of my textbooks, 23.4, but I usually go 23.5, 23.5 degrees. And that's gonna be a test question. So if angles can be a tricky thing, I think. So this would be 0, and then 23.5 degrees. That's kind of what this angle is right here. Okay. There we go. From being perpendicular, it's kind of extended or tipped over 23.5 degrees. And this is what I told you, and I use the word, I think it's theta, maybe, I don't know, but a long time ago, the Earth got whacked. And it was still ooey gooey enough, but it had started to kind of have the less dense stuff rise. And that's actually, our moon is made up of kind of its less dense stuff of the Earth. So it's a part of us. The Earth's north axis of rotation is always pointed in the same direction. And this is a whole nother story. I think at the end of this notes, I kind of talk about the fact that actually, because, it's a thing called precession, it's going to keep the tilt, but it won't always be pointed towards the star Polaris. But it always has that tilt. All right, so let's talk seasons, shall we? So just a little bit ago, I already kind of told you what season did I say this is? Summer. Yeah, got 4 choices. And then this was fall. Yep. This one. Winter. Yep. This one. Yay. Yep. Now, the way it works is we have 2 solstices and 2 equinoxes. The solstices are right here. This one, you told me summer, so summer solstice. And this one over there, you told me winter, so that's winter solstice. Just two solstices. The equinoxes then must be here and here. And they are. You guys told me this was fall. Fall equinox, sometimes called the autumnal equinox. And then over here, we have the other equinox, it's the spring equinox. Okay. So, starting with this one right here, you guys told me summer. So, the summer solstice is June 21st. And I usually tell students, because I can never remember whether it's the 20th, 21st, 22nd, or 23rd, so I just kind of say June 20th through the 23rd, because the day kind of varies a little bit. So 3 months after June, see June, July, August, September. September, that must be this one. Okay, 3 months after September, October, November, December. Okay, 3 months after December, January, February, March. Okay, so that's, feel free to use your fingers. That's how you know what months that the solstices and equinoxes happen. So why is it that over here that, and I'm going to show you a video that hopefully will a couple videos, I think, to show you about seasons. Over here you can see clearly the north axis of rotation is tilted, okay, towards the sun, and the sun's got all of our energy. So you're like, dude, I know that in the northern hemisphere you're going to be warmer. But there's a couple of reasons. One of the reasons is that we have the maximum number of daylight hours in the northern hemisphere, right here, June 21st. The Earth spins, and I'm gonna, if you've ever heard of, if you go too far north in the summer, the sun's not gonna set. That is totally true. Your days and nights can totally get mixed up. If you're north of, I think it's 66.5 degrees latitude. We get more hours of sunshine, makes us warmer. And the other thing is that the sun's rays are more direct, and I'll try to kind of show you what that looks like. Okay, now you probably could with this, if this is the equator, I guess you do like this. If this is the equator, we are experiencing summer and they are experiencing winter. Okay, which kind of blows my mind, and I don't understand Santa Claus Day. Okay, but like over here, December 21st-ish, okay, what kind of season do they have?
Summer.
They have summertime. So how does Santa get around? I'm just throwing it out there, people. Okay, I know. So anyway, it's kind of a creepy thing anyway. It's the whole same thing. So we have the whole opposite seasons. All right. So on the equinoxes, the word there is equinoxes. Equinoxes equal. I don't know if you're convinced by this figure necessarily, but on the equinoxes, as the Earth spins, all distances from the equator, we call those latitudes. All latitudes, as the Earth spins, gets equal day and equal night, which 24 divided by 2 is 12. So you're talking 12. 12 and 12. 12 hours of daylight, 12 hours of nighttime. And I really don't think that you can take an egg and stand it on a broomstick. I don't think you can. That's what one little folklore is out there. But anyway, so equinoxes. So this was fall, and this was spring. Like I said, let's see if these videos, you don't look convinced. We'll see if these videos work for you. I know this says September 22nd, but again, if you have it on a test, I'd be good with September 22nd. I'd be good with September 20th through the 23rd, because I can never remember. Okay. Now, we're going to talk about meteorology after we talk about astronomy. There's a delay. Like, for instance, the hottest part of summer. When would you say the hottest part of summer is?
July.
I'd say July, yeah. July or sometimes August, depending kind of how, probably more like an air mass thing, but July. So there's a lag between when we get the rays of the sun most direct and we get the most solar energy because of the number of daylight hours. There's a lag between when it really is. And that lag, all it has to do with is, well, put it this way. Like if you have a swimming pool in your yard and you fill it up, you're probably going to wait a little while before getting in because there's a lag for it to heat up even if you have a nice sunny day. So that's kind of, and I don't know if you noticed, but is most of the Earth's surface covered with large bodies of water? Yes. So I think I've heard different numbers. Is it like 3/4 maybe? I don't know, but there's a lot of body of water. So that's what the delay is between June and July. And that same delay then happens when those large bodies of water are cooling down too. All right, what else we got? So we talked about the 2 equinoxes. And if on a test, if you put spring equinox here, I'd be like, oh yeah, I know what we're talking about. Spring and vernal are the same thing. So don't let that throw you off, okay? All right. So the word there is equal. The number of daylight hours are equal to the number of nighttime hours. You probably already got that. So the north axis of rotation is tilted away from the sun. When is that? Exactly. Very good. You got it. December 21st I have here. But again, I never know whether it's 20th to the 23rd. So December 21st, that's our winter solstice. And it would be the summer solstice in the southern hemisphere. I do. So there's been movies about it, so I'll go over here to our winter solstice. And so here's the deal, if you, I'm sure then heard that if you are above a certain latitude in December, the solstice time, then you're not going to have any hours of daylight, which we were made to have daylight. So I've heard that up there, one of the ways they get around it is they have those lamps, the UV light, to try to kind of keep them from going crazy. But if you're vampires, this is what I think I might start to say. If there's movies about this, but if you're vampires, that's where you want to be and when you want to be. Okay? I'm just throwing that out there too. All right. Okay. So we need to kind of talk a little bit of semantics, kind of how we chunk up the earth. We chunk it up with two types of lines. And I brought this in. This is a good one for weather too, meteorology. You know, it's just another globe of the earth. But you can see the so you can kind of see these lines are lines of latitude, and they kind of extend from, where's the equator? This is too busy. This is just too busy a globe. They extend from, this must be the equator. So we go north lines of latitude, and we go south lines of latitude. Okay. So like this slide says, you go, and the lines of latitude are kind of circles around the earth. So if you go clear up here to the tippy top, this little circle, which would be, I think, of more like a dot up here, that line of, that circle of latitude would be 90 degrees north. This circle of latitude would be 90 degrees south. Oh, sorry. Beginning at the equator is the word there. So poles is the word for longitude. So the thing about longitude, I think longitude long. So they are these guys, lines of longitude. They are long. And lines of longitude go from pole to pole, but they don't go the rest of the way around, because actually that's another line of longitude. Okay, so they just go from pole to pole and stop. Lines of longitude, you need to know where they originate from, because like lines of latitude, they originate from the equator and they go north and south. Lines of longitude then originate at the prime meridian, which is in folks that are in the news. I feel bad for them. I feel bad for us. Oh my gosh, don't get me started with politics. So if we find Greenwich, I'm not a math teacher and I'm not a geography teacher. All right, so here we go. And I don't know how they got to be so important. Wow, okay. So here at the equator, you can kind of see my lines of longitude. So this line of longitude is 0. And then we can go, this one is 10 degrees, it would be west. And this one is 10 degrees east. I have 20 degrees west, and I have 20 degrees east. Okay? So you're like, well, with that sort of scenario, they have to kind of keep going. Oh, goodness. They have to keep going west and east, and they have to meet up somewhere. They totally do. And that is actually the International Day of Spring. How cool is that? I was getting this globe out today, and actually, okay, let's see what that says. It says Monday and Sunday. Oh my gosh. You're over here, it's Monday. You're over here, it's Sunday. Or it could be, Tuesday, Monday, or, Thursday, Wednesday. But it's like a day apart. Is that not cool? And the reason that is, here's it. I don't know, it kind of boggles my mind. But I will tell you that that is the meetup point for the lines of longitude. Okay, so right up to that line, we have, let's see, I have to kind of keep it here, lines of longitude. Right up into that line, we have 170 degrees, let's see, gosh, I guess that would be east, and we have 170 degrees west. And then it meets up at 180 degrees. Let's just share that. I just think that is so cool. All right, east and west lines, they meet up at 180, which is the international date line. There's a little jag in the international date line, and it's on this globe, but if you look closely, you can kind of see these little jags up here. But I mean, that would have trading implications, I would think. I don't know. Back when they did the whole, and this does still kind of boggle my mind, but how can be a different day? Back when they did the Y2K, or 1999 was going to rolled over into 2000, they were all worried about what would our computers do with that going to 1999 to 1999 to 2000, and everything's fine. I got freaked out, but everything was fine. But my point was, this is a part of it, or a factor in all that. Looks like I just hid the word dateline. You probably already got that. And this is what we were talking about just a little bit ago. As the sun rises, the folks in our East Coast see the sunrise and the sunset. We did sunset first, and then we have Central, Mountain, and Pacific. So our country is broken up into 4 major time zones. But you probably heard weird stories like there's places in, I want to say Indiana, that don't change. I mean, or they don't change for, I guess that's daylight savings time. They don't change for daylight savings time, so sometimes they're with the Eastern and sometimes they're with the Central. That'd be confusing. Another time zone for Alaska. And in general, the way this works is they're broken up by lines of longitude. So about approximately every 15 degrees longitude, you need to go ahead and hit another time zone. That's how that works. And that's all related to the whole 24 hours to complete one spin on this axis of rotation. All right. What else we got? Oh, for us, we are about 40 degrees latitude north, and the closest way to get to us from the prime meridian is to go west, and you would go about 91 degrees west longitude. Good to know, good to know. So, in astronomy, or in weather, kind of a weather thing kind of goes with astronomy. It also goes with, of course, weather, meteorology. But it's nice to have some important lines of latitude marked. And you've probably heard of some of these. So we have, and they come in pairs. So here, this is, of course, north, and this is south, lines of latitude. We have the Arctic Circle, and we have the Antarctic Circle. So they kind of come in pairs. The Arctic Circle, they're both 66.5 degrees. The Arctic Circle is north, the Antarctic Circle is south. And then we have kind of another little pair that goes together. We have the tropics. And the tropics are going to be 23.5 degrees north and south. The 23.5 degrees north is Tropic of Cancer. And to get Cancer and Capricorn figured out, I think we get corns on our feet, on our toes, or whatever. So Tropic of Capricorn is in the southern hemisphere. So those are, and so you figure, I told you, what latitude are we? We're 91 west longitude. What are we latitude wise? About 40, yeah. We're about 40, so we're between those two important lines. And then last but not least is your zero latitude, and that's your equator. was hoping to get to videos. Let's see what's on the next slide. Okay. So I want to show you at least